place. So today I'd like to talk about the Goldstone mode closed or the open system. And the talk is based on the work published around 2019. So anyway, so I'd like to tell you about something interesting about the Goldstone mode dynamics in such a setup. So let us start from the beginning, but before going to the topics, that I'd like to first introduce myself, because I find many people that I'm meeting for the first time. So I'm from the Niigata University in Japan, and this is Japan, and we have the Tokyo here, Osaka here, and the Niigata is around here. And one advertisement is that we have the Sado Island, which is very famous for the gold mining, and recently recognized as UNESCO World Heritage. So anyway, if you have a chance to visit Japan, please come to our university or somewhere in Niigata or in Japan. And I'm from the high energy physics, so originally I was working on the clock-long plasma physics. And the main research interest is like the derivation of the hydrodynamics from the quantum field theory or thermodynamics. And also I was working on the effective field theory or the Nambu-Goldstone mode, or also recently I'm working on the EFT treatment of the universal feature of the quantum field body physics. So then today's talk is mainly about these first two topics, like the hydrodynamics or the Goldstone mode from the viewpoint of the effective field theory. So let us start from the very beginning. So what is Nambu-Goldstone mode or Nambu-Goldstone theorem? So this is the result obtained around the 1960s. So originally the original Nambu-Goldstone theorem says that if you have the spontaneous symmetry breaking in the relativistic system, you inevitably have the gapless propagating model, which propagates with the speed of light. And this gapless mode is known as the Nambu-Goldstone mode now. And also there's the statement that the number of the Goldstone mode is equal to the number of the broken symmetry, so that we now have the counting rule for the relativistic system. But if we consider the non-relativistic system, that there are also the many examples of the Nambu-Goldstone mode in condensed matter physics. For example, if you consider the superfluid phonon, and then in this system, the U1 symmetry is spontaneously broken down, and the macroscopic behavior is completely or drastically changed, and we have the superfluid dynamics in such situations. And if you consider the spin system, the SO3 symmetry is broken down to the SO2 symmetry by having some specific direction of the spin. And then we have the behavior, something like this, and we have now the ferromagnet in this system. And if you focus on the more detailed, like the dispersion relation, whether we have how many number of the Goldstone modes are there, then there is a slight change, slight difference. So in this case, that we have the superfluid phonon is the linear dispersion, and which is propagates through with some speed of some velocity. And the number of the Goldstone mode is the same as the number of the broken symmetry, because we have just one mode, and the broken symmetry is U1, so that the number of the broken symmetry is 1. But in this case, the ferromagnet case, the situation is slightly different. And indeed, what we have is not the linear dispersion relation, but we have the quadratic dispersion relation. And also the number of the Goldstone mode is different from the number of the broken symmetry. And so that means that we have this change, or we have the modification of the Goldstone theorem in the set of in the relativistic setup, if you want to apply it to the non-relativistic case. And such an extension is I think indeed how to say investigated roughly 10 years ago. But before going to that, I would like to say that what is a spontaneous symmetry breaking from the viewpoint of the QFT. So if we have the continuous symmetry, that means that we have the conserved charge according to the Noether theorem. And then the definition of the spontaneous symmetry breaking is like this. So if you need to have some kind of a field operator whose expectation value, the expectation value of the symmetry transformed one is non-vanishing. This gives us the kind of the definition, formal definition of the symmetry breaking. Also, we need to have the careful treatment of the limit involving in this expectation value. And there is indeed a classification of the Goldstone mode in the non-relativistic system, which is obtained by the Yoshimasa Hidaka and also the Watanabe and Murayama around the 2012. And one is the very, how to say, what is the usual Goldstone mode, which is called the type A Nambu-Goldstone mode. And in this case, that all the expectation value of the commutator of the charge is vanishing. And in this case, that you have the so-called type A Goldstone mode. And in this case, that also we have the counting rule. So number of the broken symmetry is matching with the number of the Goldstone mode. And also we have the linear dispersion for this case. But if you consider the different case, so I mean that there is a case called the type B Goldstone mode. And in this case, there is a charge whose commutator is not vanishing. And in this case, we have the type B Goldstone mode. And the number of the broken symmetry is different from the number of the Goldstone mode. And also it often shows that the quadratic dispersion rather than the linear dispersion and so on. So there is indeed established result for the Nambu-Goldstone theorem in the non-relativistic system. And if you recall that our case, that in the superfield form case, that we have the U1 symmetry, which is broken down, and then we just have one charge, so that we do not have any non-vanishing commutator. That means that we have type A Goldstone mode in this case. On the other hand, if you consider the ferromagnet, so we have the SO3 symmetry, which is broken down to the SO2, and the ferromagnet has the non-vanishing spin expectation value along some direction. And let us choose the Z direction in this case. And then that means that we have the commutator, the non-vanishing commutator between the spin, and these are indeed charge associated with the SO3 symmetry. So that means that this is the ferromagnon is regarded as a type of B Goldstone mode.
But in the anti-ferromagnet, it's also true that you break SO3 down to SO2,
yes.
But you actually have what you would call 2 type A. So
yes, exactly. So so this is the case for the ferromagnet, and if you consider the antiferromagnet, the spin expectation value is vanishing, so that the antiferromagnon is classified into the type A Goldstone mode as recalled correctly. Thank you very much. And then the question of my talk is following. So what happens if we consider Goldstone mode at fine temperature or the more exotic setup? And especially I'd like to understand how Goldstone mode behaves in a kind of the more exotic setup, like this or this. And the first setup is a more kind of the conventional one, that we are just considering the equilibrium system and at fine temperature, and we can consider what happened or what is the dynamics of the Goldstone mode at these situations. And the more exotic situation is like this. So we can consider some non-equilibrium open system, and in this case, the situation is completely different from this one, and something very non-trivial happens. And there are several work related to these situations, and you can if you are interested in, please refer to this work, and there are several ones, and also I think that in the non-equilibrium open system case, and Minami and Hidaka's paper around 2015 is very, I think the pioneering work, which it contains a lot of the results, and you can enjoy reading this work if you are interested in. And anyways, what I would like to show you is that, so depending on the situation, that you may have the so-called type A or type B Goldstone mode, and it may show the diffusive propagation, the distribution procession, or in the non-equilibrium open system, you may also have the diffusion with the gap damping, which is completely different from the usual Goldstone dynamics. So anyways, let us go on. So this is the outline of my talk. So I finished my motivation. That I would like to understand how the Goldstone mode appears and how Goldstone mode behaves in the fine temperature system or the open system. And I will explain the one theoretical way to describe the disclosed system at fine temperature or the non-equilibrium open system. And let us start from the more kind of conventional system, that is equilibrium finite temperature system. So the situation is like this. So if you consider the equilibrium state, we have this behavior. And because we are considering the closed system, the important point is the charge is indeed conserved by definition. And then the point is that the charge is indeed conserved even when the symmetry is spontaneously broken down. So that means that if you consider the slight generalization of this equilibrium setup to the non-equilibrium one, then we may have this kind of a picture. That means that the hydrodynamics should be a universal low energy theory that describes or that captures the dynamics of Goldstone mode at this finite temperature setup. So then the question is, how can we derive the hydrodynamic equation in such a the symmetry broken situation? And that is the first point that I would like to explain in this talk. So there are several frameworks, and the more, how to say, the recent, one is known as effective field theory. I will explain later. But I would like to first show the very old-fashioned derivation of the hydrodynamic equation just based on the thermodynamics of the irreversible process. So let us start from the very simple situation. So this is the prototype example of the hydrodynamic in the normal phase. And I'd like to now describe the charge diffusion. And in this case, we just have the single conservation law like this. And then let us start from this kind of the local, how to say, the inhomogeneous charge distribution setup and start the real-time evolutions. And what we expect is that, okay, so if we are considering the generic system, not the integrable model and so on, then what we expect is that the charge flows according to this law, and then the charge inhomogeneity is relaxed under the time evolutions. And such a behavior can be captured by postulating the so-called constitutive relation, which relates the current J to the charge N. And the important point here is that unless we specify this constitutive relation, we cannot solve conservation law because we have the equation for N, but the J is, they should be expressed in terms of N. Otherwise, we cannot solve this equation. And such a relation can be given by the constitutive relations. And also, we need to know what is the value in front of these something. And this kappa is regarded as a charge conductivity, and the chi is regarded as a charge susceptibility. And by identifying all the three ingredients, we can now solve the hydrodynamic equation or the conservation law to find that there is a diffusion behavior like this. So this is indeed, this indeed describes the gapless mode because as you see from this one, just linearized analysis gives us this dispersion relation, so that even though it is not propagating, that this mode describes a gapless mode, so that it will play a central role in the low energy behavior. And the point of this discussion is that there is no, how to say, the time reversal process appearing. I mean that happen spontaneously. So that means that to derive the hydrodynamics, we can rely on the phenomenological structure like this. So there is a no-go for the time reversal process. That tells us that probably the thermodynamic concept, and especially the second law of thermodynamics, should play the central role to derive or identify the hydrodynamic equation, well, more precisely the constitutive relations. So this is I now explain how the thermodynamic concept is used to find the constitutive relations. So here we first need to start by determining what is the dynamical degrees of freedom in our theory. And of course that is the charge density because we are considering the hydrodynamic conservation law for the equation of motions. And then what we need to do is we need to identify how we can relate J to the charge density N. And then in the second step, we can introduce the entropy, which depends on our dynamical variable. So now the entropy density is regarded as a function depending on our charge density N. And then we can also introduce a conjugate variable, and this describes the local chemical potential. And then we can write down all the possible terms with finite difficulty. But the point is that we need to restrict some terms to be compatible with local second law, meaning that we have the current, entropy current, which satisfy this positivity constraint everywhere in our space-time. And then we find that some constraint appearing that the charge conductivity should be positive, and also the entropy current is identified as this one. And this is one way to derive, phenomenologically derive the constitution of the hydrodynamics. So then let us apply this reasoning or this framework to the symmetry broken system. So I'm now considering the simplest case that the system breaks the U1 symmetry. And this means that according to the Goldstone theorem, so we should have the Goldstone model in the description of the low energy or long time behavior. And then that should be the superfluid form. And so we need to take into account the superfluid form dynamics as well as the charge density dynamics. So how then the thermodynamic framework works? So this is what I showed already in the case of the normal fluid and or charge diffusion. And then let us restart the same analysis for the superfluid case. And our dynamical degrees of freedom is given by the charge density n. And also I added the Goldstone model pi. And the point is that so this equation motion follows just from the Wald-Takahashi identity or just the symmetry. And in addition to this equation motion, we should have the equation motion for pi, Goldstone mode, so that I have the two unknown. So one is the current Ji and another unknown quantity is given by this capital pi. So I need to identify the form of Ji and pi in terms of the charge density n and also the Goldstone field pi. And then I introduce the entropy, which is a function of the charge density n and also the Goldstone field. And here I use the information from the symmetry. I mean that the spontaneous symmetry breaking of the U1 symmetry restrict us to construct the entropy as how to say the U1 invariant quantity. And the Goldstone field pi, the transform as a shift under the U1. Then we should use this quantity, the gradient pi square, which could appear as an argument of the entropy. Then I define the conjugate variable, local chemical potential, and also the condensate F in this case. Then I require the second law of thermodynamics and local law. I mean that we should have the entropy current which satisfies this positivity constraint. And then after some calculation which is not so difficult, we can just find that this constitutive relation would satisfy this entropy positivity constraint. So we also identify what should be the entropy current in this case. And this is the way, please go ahead.
Why is mu just del I pi squared and not?
Say it again.
Why is mu del I pi squared? Like, can you not have pi dot or something else?
So maybe
So you said mu, S depends on n and mu, and then mu is just del I pi squared.
So point is that so we need to identify how Goldstone field transform under the U1 symmetry. And under the U1 symmetry, the Goldstone mode pi acquires just a constant shift, something like this. And this is a constant. So that I need to make the entropy to be the invariant under this symmetry transformation. I can use now the gradient pi. And then because according to the rotation symmetry, we may take the square, and that could appear in the argument of the entropy. And that is, I think, constraint by the symmetry. Just
pi dot is also.
Oh, the entropy is defined as some constant time. So that should be defined by just a spatial derivative rather than using the time derivative. So.
Sorry, can I ask a question as well? So I'm a bit confused about why you're allowed to have a term with no derivatives on the right-hand side of the continuity equation for pi, because naively I'd have thought that you add up pi over all space, it's just telling you what the vacuum is. Like.
Okay, so this is important point. So indeed, in applying this second law of thermodynamics, we find that the non-trivial cancellation between this first term in J and also this first term in pi. And they are required to be both in these constitutive relations. And And if we neglect these two terms in the these two second terms, then the entropy is indeed conserved, meaning that so in neglecting this term, we have the superfluid dynamics without dissipation.
So is the superfluid sort of, is there a sort of Josephson oscillation or something that's associated with mu?
Exactly. So that is what I would like to show in this slide. So this is a result. So I have now equation motion, and it is equipped with this constitutive relations. And if we see that this equation, this means that we have the supercurrent proportional to gradient of the phi phase. And the second term describes the diffusion of the charge. And for the constitution for pi, I find that this first term, and if you combine this equation with this one, you find that this is nothing but the Josephson equations. And in addition, that the equation allows us to have this damping effect, which is proportional to the square of this phi. So here we now have the two Onsager coefficient phenomenological parameter, which should be the positive according to the second law of thermodynamics. And these two coefficients are regarded as a kind of the low energy parameter for our effective field theory, which is a superfluid EFT.
Can I also ask, so go back one slide. How do you actually do step 3? Like, it seems fairly, it's not obvious to me how.
Oh, I see. So it is indeed very simple, so procedure, because according to the step 2, we already assume that S should be the function of N and the V. And then we can take the time derivative of S, and this should be, just using the chain rule, we can just write this as the derivative of the N with respect to, S, S, N.
Oh, I see. And you use the equation of state to work out the functional derivatives.
This is our definition of the beta mu, and this is we can use for the equation of motion. So that this is very simple exercise.
Okay, cool. Thanks.
Maybe 3 minutes or so. So anyway, so this is the derivation of the thermodynamic derivation of the superfluid dynamics. And this is, indeed, describes a non-linear dynamics. But if we linearize this set of the equation, then you can find the normal mode. And we just find that there is gapless mode, which have the diffusion behavior. So this is the schematic picture of the dispersion relation. The blue curve describes the real part, so that we have the linearly propagating mode. And this red dashed curve shows that the imaginary part, so that we, in addition, have the diffusion behavior for this Goldstone mode. And even though I just consider the U1 symmetry, so you can now generalize this kind of discussion to the more trivial case, like the type B Goldstone mode and so on, with some technical, small technical difficulty. So anyway, this gives us a kind of the derivation of the the description of the Goldstone mode in the final temperature setup. So this is what I now shown. So we just use the thermodynamic relation, and so this part I will explain soon. So anyways, I find that this kind of energy spectrum for Goldstone mode. And before going to this non-equilibrium open system, I'd like to explain something, just to do a kind of the one-page detour to the stochastic fluid. So there's just a one page. so here is the set of the equations that we derived based on just the thermodynamic law. Just we use the first law of thermodynamics and second law of thermodynamics. And but the problem is that this just describes the average dynamics of the hydrodynamics. I mean that the conserved charge. And in the realistic setup, we have the average dynamics, and on the top of that, we may have the small fluctuations thing there, so that so if we are also interested in the dynamics of the fluctuation, we should update or promote this equation to be the stochastic one. And such a stochastic promotion is somehow almost unique by if you just assume that the fluctuation dissipation relation should hold. And this fluctuation dissipation relation indeed guarantees that we have the correct long time equilibrium probability distribution for this system. So now these variables are all having some kind of the resting check regarded as a stochastic variable, And then we have the noisy constitutive relation having also the noise in here, and also there is noise in here. And these noise are assumed to satisfy the fluctuation dissipation relation. So that 2-point function of these quantities should be related to this transport coefficient or Onsada coefficient. And the point here is also that the Onsada coefficient, kappa n and theta s, they should be regarded as a kind of a bare coefficient from the viewpoint of the QFT. So if you compute the loop, then there is a loop correction even for these quantities, so that we need to perform the kind of the renormalization procedure to these quantities. So anyway, the motivation or the advantage of this stochastic version is that so this stochastic update allows us to have the kind of the path integral formalism. Such a path integral formalism would be somehow very useful because it gives us defined kind of the effective Lagrangian for the Goldstone model in the ideal dynamic system. So this is very, I think, the high energy, how to say, the people prefer way to consider the dynamics. So once we fix that symmetry, then we can construct the Lagrangian which governs the dynamics. And this kind of the stochastic promotion would enable us to construct such an effective Lagrangian, which is indeed known in the statistical mechanics community as the MSR JD effective action. So, and if you are interested in such a direction, that maybe from the fluid theoretical viewpoint, I would like to recommend you to read the lecture note by Pavel, published around 2012. So that is very nice, lecture note. Anyway. So then after this let us now go to the discussion of the non-equilibrium open system, which have the, how to say, more kind of the technical, have the kind of the interesting behavior. So now the situation that we want to consider is something like this. So we want to describe this system, open system, which is coupled to the environment. And there would be a pump and loss between them. And the important point here is that the charges are no longer conserved in this setup, because it can simply escape to the environment. So that seems to be very important part, because so if you consider this situation, then the notion of the symmetry is slightly, how to say, very tricky. So we need to identify whether the notion of the symmetry and its spontaneous breakdown is well defined or not. And also if this question is, we can correctly identify what should be the symmetry and the symmetry breaking pattern, then we can probably have the Nambu-Goldstone mode. And if we have the Nambu-Goldstone mode, the question is how it behaves in such a setup. So this is the question of the main.
One question. I mean, when you say pump and loss, I mean, it's just energy, or you can pump anything, or I mean.
Okay, so there should be once most clear one is the energy or the momentum. But if you consider some symmetry breaking for the U1 symmetry, then the number could be diffused into dumped into the environment, and any other conserved charge would be regarded as a
No momentum in your hydrodynamic equation. Right?
So far that we do not have the momentum. So we just focus on the internal symmetry rather than space-time symmetry. Case. So any other questions? Okay, let us now clarify what I want to do. So here is the setup, so microscopic setup that we may have the total system. And the total system is composed of some system degrees of freedom and the environment degrees of freedom. And they have their own action part, and also they also have the interacting part. And I assume that this total system is invariant under the G symmetry. And then if we specify some microscopic model, like for example, if you write down for example, the Lindblad equation, then the energy or the spin or the number is not conserved in such a setup. And then such a Lindblad equation is regarded as a microscopic model. And then suppose that in total we may have G symmetry, but if such a G symmetry is spontaneously broken down, which I will clarify soon, then we may have the Goldstone mode, and in the macroscopic level, the low energy dynamics, the long time behavior is governed by the Goldstone mode. So I would like to understand how we can construct the effective field theory for this Goldstone mode in open system. This is a question I would like to understand. So the problem is that this is not the zero temperature system, and also this is not the equilibrium system, meaning that we have the non-equilibrium steady state described by the, say, the Lindblad type equation or the Fokker-Planck equation or something like that. And also it have the dissipation because we have the pump and loss from the system to the environment. And to describe such a situation, we can now rely on the Schwinger-Kelch formalism from the microscopic viewpoint, or you can also rely on the MSRJD functional formalism in order to describe this setup. So then I will now explain, introduce a notion of the non-equilibrium effective field theory in a nutshell. So the very basic part based on the pioneering work by the Grossi, Glorious, and Liu. And here the Liu and Glorious, this is a kind of lecture note, so you can learn many things from this lecture note. And this is our, let's say, the application of such a formalism to the open system Goldstone mode. So anyway, let us start from the basic formulation of the Kelch formalism. So here is a one-page summary of the Schwinger-Kelch formalism. And in the usual QFT at zero temperature, what we are interested in is this kind of the quantity. So we are usually considering the transition amplitude. For example, the example of such a observable is that this S matrix, so which is not indeed observable, so it should be the square. So anyway, so this kind of the transition amplitude is that we usually compute in the QFT course, and such a transition amplitude can be computed from these generating functions. So we have the vacuum, and we introduce the time evolution operator under the external field J, source field J, and then we have the vacuum. Then this by taking the functional derivative of this quantity with respect to J, you can find the arbitrary transition amplitude. That is a way that we run the QFT course. But in the non-equilibrium setup, if you are interested in real-time dynamics of quantum system, the observable that we are interested in is the average value or the correlation function, real-time correlation function, so that we need to have consider this kind of the torus over the, say, the initial density operator, and because the time evolution have the structure that is sandwiched by generated by sandwiching the operator with the U and the U dagger, we have the most useful quantity or useful generating function is defined as a closed time path generating function, which has a forward time evolution and backward time evolution under the presence of a different source field. So this is a very useful theoretical tool to compute the quantity in the Schwinger-Kelch formalism. So the important point here is that by construction, that this generating function satisfy a set of the constraints, and that is indeed clarified by the Hongo and so on, and the collaborators. And the basic property is something like this. So the first part is very non-trivial. So we may have the double symmetry. Maybe I missed a type. So this capital J and this small j is the same source field, external field. So the point here is that if you have the symmetry, then we may have the double symmetry, which makes this generating function to be invariant. But there is a subtlety that I will mention soon. And the second condition is very trivial. So if you take this external field to be the same, then if we have the U dagger U with the same external field, so that it will cancel each other, so that we just have the torus rho zero in this setup, and which is normalized to be 1 by definition. And then we may also have the reflectivity condition, which is coming from this structure. And if the initial state rho 0 is the thermal density operator, you may also have the KMS condition for this generating function. So this is, I think the set of the constraint for the closed time path generating function. So how we use this constraint, and this is what I show now. So suppose that we are now interested in this closed time path generating function, and it is defined by integrating out all the microscopic degrees of freedom phi 1 and phi 2, which I wrote here. And what I would like to do is I would like to integrate out all the UV mode, all the massive mode, and just keep the gapless Goldstone mode. And then if I can do this kind of things, what I have is the so-called effective action for the Goldstone mode in this way. And the point is that because of the set of the constraints that the closed time path generating function satisfies, we can to make it explicit, we can assume that the property of these effective actions. So these are the set of constraints on the effective actions, which guarantees that this generating function satisfy indeed the set of the constraints that I showed in the previous slide. So the first constraint is so we need to satisfy with respect to the double symmetry structure, which I explained. And if we are in the symmetry broken phase, we need to introduce a Goldstone mode as a nonlinear realization of the symmetry. And the second one is that somehow trivial, and I turned off all the external field. And if pi 1 pi 2 is equals, that should be 0. And if this condition satisfies if we take the same argument for this double external source, then we have the trivial condition for such a behavior. And we may also have the reflectivity condition for the effective actions. And also for stability, I assume that the positivity constraint, that the imaginary part of this action should be the positive definite. So these are the set of the constraint. And by assuming that these set of the constraint and applying this formalism, I write down all the possible terms which satisfy these constraints to construct the effective actions. Then you can find that the most general actions which can describe your low energy dynamics. And that is indeed applied to the closed system and indeed reproduce the MSRJD functional for the stochastic hydro. So that is obtained in the Hongo paper. And also they have the kind of the generalization that allows us to keep the quantum correction, which is absent in the MSR method. So anyway, this is just a case for the closed system, and then let us apply this formally to the open system after clarifying the symmetry structure of this open system. So the point is like something like this. So we expect that there is double symmetry structure. So that means like this. So this is a situation that we are now considering. So this is a generating function which we are now considering. So that we have the system degrees of freedom phi 1 and phi 2, and also the environment degrees of freedom sigma 1 and sigma 2. So that we have the path integral expression of this quantity. And because I'm interested in the dynamics only in the open system, I now integrated out the environment degrees of freedom to obtain the effective action for the system degrees of freedom. Then the point is that so if you see this part, so this part contains all the degrees of freedom which we are now considering, so that this system conserves the energy and other conserved quantity. That means that of course there is just I assume that the G invariance of this total action, so that this part and this part are separately invariant under the symmetry transformation which I wrote here, the G1 and the G2. And but in the conserved system, the point is that the rho 0 breaks one of the symmetry, so that we only have the diagonal part of the symmetry that we wrote as the GA here. So anyway, but now the situation is slightly different. Now we are now considering the open system, so that after integrating out environment degrees of freedom, we have this effective action, induced effective action for the system degrees of freedom. And then because of the presence of this gamma, these combinations just enjoy the invariance under the diagonal part of the symmetry, GA symmetry. And yeah, I recently learned that these now they're called the strong symmetry. I think the GR is identified as strong symmetry. And this GA, the diagonal part of this double symmetry is called the weak symmetry, I think. And the point here is that, so even if we consider this open system, we have the remaining weak symmetry, GA symmetry, so that we can consider the spontaneous symmetry breaking of this weak symmetry in some steady state of our open system dynamics. So, but before going to such a the direction, I'd like to just sketch what is indeed say that we indeed have such a symmetry in the simple Brownian particle system, Brownian motions. So this is the situation. I have the Brownian particle which coupled to the surrounding the lighter particle, and here this is the generating function. We have the Brownian particle and also the lighter part set of the lighter particle. And if we assume that this lighter particle is just a set of the harmonic oscillator, we can integrate out all the harmonic oscillator to obtain this effective actions only for this Brownian particle. And we also take some kind of the low energy limits that allow us to have this dissipation for the Brownian particle, which is characterized by this gamma. And now that we have the diagonal component and the non-diagonal part, and this non-diagonal part breaks the symmetry. So some symmetry.
Sorry, what are you doing here? Like, what's the symmetry? What's being broken?
Okay, that is I will now explain. So in this case system, the effective action after integrating out environment fields like this. And the point here is that this Brownian particle enjoys a time translational symmetry.
I see.
So that means that even though the energy is not conserved, we have the time translation symmetry.
But it's a weak time translation symmetry.
Yes, exactly. Weak time translation symmetry.
Sorry. So here you have assumed ohmic bath to get.
Yes, exactly. So here this simplification occurs if we assume the ohmic bath, so that we have the well-defined dissipations here. And then the point is like this. So we have this Brownian particle system, and of course, the energy is not conserved in this setup because we are just focusing on this Brownian particle. That means that this strong GR symmetry is broken, explicitly broken. But we have the weak symmetry, GA symmetry, and this is somehow, so we have the conserved quantity, which is identified as a Fokker-Planck Hamiltonian, because the Fokker-Planck Hamiltonian generates the time evolutions in such an open system setup. So that even though we do not have this strong symmetry, we still have the GA symmetry, weak symmetry, so that we can consider the spontaneous symmetry breaking of this weak symmetry. That is what we consider in the paper.
So what do you mean by weak symmetry?
Oh, that is just a recent terminology. I think that I call that this as a GR symmetry and this is GA symmetry, and this describes the diagonal part of the double symmetry. Yeah. And I think I don't know, maybe the quantum computation guy, maybe.
I mean, you can roughly think that like the strong symmetry is conserved on every trajectory, and the weak symmetry is average.
This is probably the strong symmetry, and this is the weak symmetry. Is that right?
Yes.
Yeah. Okay. Thank you very much. So then these are the basic formation, and let us apply this formula to the spontaneous symmetry breaking in open system. So the point is that we need to construct the most general effective Lagrangian for the energy mode in open system by assuming that we have indeed symmetry breaking for the weak symmetry. So this is assumption. So we assume that the steady state is only invariant under the subgroup of this weak symmetry GA. So I now assume that the HA, the Lie group GA is broken down to the HA, so that the symmetry breaking pattern is like this. And so we have indeed kind of the established formula to describe the general effective Lagrangian from the 1970s, I guess. And this is called the Karan-Coleman-West-Zumino method. And which are also called as the coset constructions. The point is that we can identify the Goldstone mode as a kind of the symmetry breaking parameter, symmetry transformation parameter, local symmetry transformation parameter. And here, yeah, very technical detail starts. But anyways, I just show the result. So we can introduce the so-called Goldstone field for the doubled symmetry. So we now introduce the Goldstone field pi1, pi2 in this coset space. And I use parameterization like this to have the diagonal part and the kind of the non-diagonal part. And the most important point is that we now know how they transform under the GA symmetry, weak symmetry. And these are governed by the definition. That means that these quantities are indeed belonging to the coset space. So once we identify this symmetry transformation rule, we can now write down all the possible terms which satisfy the constraint also following from the Schwinger-Kelvich formalism, the structure of the Schwinger-Kelvich. Then the point here is that this pi r is, indeed non-linearly realized this GA symmetry, while this pi a field is a kind of the adjoint representation for the GA symmetry, so that we can now write down all the possible terms. And in order to write down all the possible symmetry invariant, GA invariant term, it is quite useful to introduce the so-called Maury-Kaltan-Wan form, and which is defined like this. And the point is that we can decompose the perpendicular or parallel part of this one, because this alpha pi r belongs to the Lie algebra of the GA symmetry. So that we can now decompose it into the broken part of the Lie algebra or unbroken part of the Lie algebra, and which shows that the nice transformation rule according to these coset constructions. And then anyways, we can write down all the possible terms which satisfies all the constraint and the symmetry constraint. And we assume that the two approximations here. So the first approximation is that we assume that the fluctuation expansion, so that we just keep the effective Lagrangian up to the order pi a square. That means that we are considering the effective Goldstone mode dynamics with the effective Gaussian white noise. And we also assume that the derivative expansion, and we keep all the possible order p square term, and then write down the effective Lagrangian. And a little very complicated. And I just write down the linearized one. So here, after the linearization, I find that this effective Lagrangian up to the pi square, or the pi square. Then the point here is that there is a set of the low energy parameter, or low energy coefficient, and there are some terms which are already existing in the closed set system setup, and these magenta quantities are peculiar to the open system setup. And here is just a notation that you do not need to take seriously. But anyways, we can write down the effective Lagrangian, and the point is that we can now find that what is a retarded green function for this system. And because also before doing that, here is a proposal to classify the Goldstone mode in open system, and I follow the convention in the usual closed system setup. I assume that if all the m alpha prime is equal to 0, then I say that okay, this should be the Goldstone mode, type A Goldstone mode in open system. And if one of the parameters, if there exists some parameter which does not vanish m alpha, then I assume that I call that this as a type B Goldstone mode. And this is because this parameter m alpha prime is indeed proportional to the expectation variable charge commutator in the closed system setup, so that this generalizes the notion of the symmetry breaking pattern or the classification of the Goldstone mode in open system setup. But the one, I need to mention that in their paper, Hidaka and Minami's paper, that they use a slightly different notions. I think they define the type A and type B Goldstone mode in a different way. So I'm really sorry for the confusing notion. But anyway, this is our way. And the point here is that we have the retarded green function sitting here. So in the Schwinger-Kelvich formalism, here is retarded, and here is advanced, and here is the symmetric Green function of inverse. So that once you find the inverse of the retarded Green function, you can now find the energy spectrum of Goldstone mode by solving the characteristic equations. So then we can just find the pole locations, just solving this characteristic equation. And the result is like this. So here I assume that some certain parameter is vanishing. And in this simplified setup, that we find that the spectrum is like this. So we have the one gapped mode and also the another diffusion mode, gapless mode. And in the type B case, so we solve this setup by assuming that simplifying the situation by assuming that these one to be vanished, and we find that these one. And here is the gapped mode, and here we have the diffusive precession mode. So this diffusive precession mode is slightly different from the one we obtained in the closed system, because here the imaginary part appears even at the k-square order, which is different from the usual situations. So we can now write how it behaves by changing the parameter. So here is the energy spectrum of the type A and type B Goldstone mode. Here is the type A limit. So we have the gapless mode sitting here, which does not have the real part at the soft momentum limit. And here is the gapped partner sitting here. And if you change, or if you introduce a finite parameter m, then we may have the splitting of these modes to be like this. So we have the different behavior at the softer regime. And there is very, please.
Are these modes stable against fluctuations?
Yeah. Yes. Yeah. So I think, in some sense that we assume that because the stability condition to respect the stability condition, we assume that the imaginary part of the S should be positive. That is the first point. And another point is so gamma. So if gamma is non-negative quantity, so non-positive quantity, then we may have the instability. So that maybe the precisely speaking that we assume that gamma should be the positive, so that the situation is stable.
But I'm thinking of a paper from Ehud Altman and Sebastian Diel, who I guess will be here soon, where they studied fluctuation correction status, and I thought there was KPZ.
I see. So okay, that's a good point. I would like to say something. So
I mean, this is not two-dimension specific, right? That result, the KPZ issue, is like specific to two dimensions. Whereas I think you're doing things in arbitrary dimensions.
That's also interesting. But the point is that so if
I think their thing wasn't any. Yeah, you're right that their paper was about two dimensions.
In high dimensions, the KPZ nonlinearity is weak. It's sort of irrelevant if it's weak.
Right.
It's
But in
sort of
1D,
goes away.
2D.
Yeah, in 1D or 2D, I think this story gets modified even further.
Okay, so we'll assume you're in 3D.
And indeed there is a term which is responsible for the KPZ coupling, so that if you consider the lower dimensional system, then this linearized analysis would break down because of some large fluctuation effect coming from such a term.
Sorry, can I ask a question? So, what is the definition of gap? So, in the case of type A, when k goes to 0, the omega is minus I x squared gamma. So, it's non-zero means gap.
Yes,
so it's pure imaginary.
Pure imaginary, yes, exactly.
Even if it's pure imaginary, if you have some non-zero value in the limit of k goes to 0, you say it gap.
Yeah, so that is my notation.
Can I ask also? So in the type A, so that would be like, so why isn't there a linear piece that is real in the?
This is John.
No, there. So you are considering just the pure diffusion case, no? When you say U1 spontaneously generating, it's not like it's not a superfluid. Say, is it correct?
Oh, so here is the situation for the open system case, and if you consider the closed system limit, this gap is this window is shrinking, and eventually it closes, and then you reproduce the Goldstone mode in the superfluid case. So here because of the open system nature, that we have the non-propagating mode at the soft momentum limit. So did
Yes, so I'm trying to understand. Gamma is your parameter that controls how open the system is, right?
Exactly.
And so,
So, so this gamma, this magenta term is very peculiar to the open system. So by keeping this gamma, then we have the not the close. Yeah, this term breaks the one of the strong symmetry explicitly, so that we have the gap for the. Yeah, I mean that that makes the diffusion mode for the soft momentum limit.
yeah, but so how do I see when gamma becomes very, very small, how do I see that I recover from those dispersion relation that I recover what I would expect?
Thank you very much. So this is in this limit that I indeed take the k to be small, and if you consider gamma zero limit, then you cannot take this limit. And what happens is that this window is proportional to the size of the window is proportional to gamma. So if you take gamma to be zero limit, this window is shrinking, and then it merges, and then we have just the imaginary part and the linear dispersion.
So you are working in a regime where k is smaller than f squared gamma. And so that's a scale that also suppresses the k to the fourth and so on. And so can you trust the first mode? Because it looks like
You mean that this
it's decaying
yeah,
as fast as your cutoff.
Yeah, I think that is
The gap, what you call the gapped one, no?
yes. This mode is indeed gapped mode, so that if you just take the soft momentum limit, you can just find that this single diffusion mode. That would be the case, but we here keep the both mode in the setup. So yeah, it depends on how you consider the soft momentum limit.
5 minutes.
Oh, yes, thank you very much. And here there is indeed very intuitive understanding of these behavior. So these are the spectrums that we obtained, and here is a type A limit, and here is a type B limit. And we may have the very simple understanding based on just mechanics. So suppose that we consider some particle which is connected to the spring and having the fixed end, and then we also consider the effect of the air resistance, and then let us consider the oscillation of this particle. What happens is that we have the two directions which particle can move, and depending on the parameter, we may have the overdamping behavior or the damped oscillation behavior. And indeed, if you see that this type A Goldstone mode case, we have indeed such a case, because so here in this shade, gray regions, we have the real part and the imaginary part, and that says that this is the behavior is basically the damped oscillation at this region. And if you see that this the window regions, and then we only have the imaginary part, so that this region is regarded as the overdamping region, and in between them there is a critical damping region which can be regarded as an exceptional point. And for the type B case, it is there is a slightly, technical setup. We attach the charged particle to the spring and apply the magnetic field and consider the dynamics under the air resistance. And then we have this kind of precession motion, and such a precession motion, damped precession can be regarded as this behavior around here. And here is the possible setup, physical realization of the setup. We may have the driven dissipative BC or the dissipative phase marginal and dissipative phase marginal. So that may realize the source momentum regime. So here is the summary of my talk. I find that I can now describe the Goldstone mode in the closed system or open system, and they may show that these kind of the funny spectrum. So and there's an outlook, but I will skip this part. And the point is that also the Ricardo Penco will give us a talk about the open system Goldstone mode in the last day of the workshop. Okay, thank you very much.